Start by understanding what a solution really is. In chemistry, a solution is a homogeneous mixture where one or more substances, called solutes, are uniformly dispersed at the molecular or ionic level within another substance, known as the solvent. The key here is uniformity. No matter where you sample the mixture, its composition is the same. For example, when you dissolve salt in water, the salt particles are evenly distributed, making the mixture homogeneous. Contrast, a heterogeneous mixture like sand and water has visibly different parts and is not uniform throughout. The solute is the substance being dissolved, usually present in a smaller amount, while the solvent is the medium that does the dissolving and often determines the physical state of the solution. This foundational concept set the stage for exploring the fascinating world of solutions. Solutions come in many forms, depending on the physical states of their solute and solvent. For instance, solid solutions like alloys involve a solid solute and a solid solvent, such as copper dissolved in gold. Liquid solutions are perhaps the most familiar. Think of sugar dissolved in water or ethanol mixed with water. Even gases can form solutions like oxygen dissolved in water or air itself, which is a mixture of gases. Classification extends to gaseous solutions, where both solute and solvent are gases, such as the mix of oxygen and nitrogen in the air. Each type of solution has unique properties and examples, making the study of solutions both broad and intriguing. Understanding these types helps us see how solutions are all around us, from the air we breathe to the drinks we enjoy. Now let's talk about concentration, the measure of how much solute is present in a solution. There are several ways to express concentration, each suited for different scenarios. Mass percentage tells us the mass of solute per 100 grams of solution, while volume percentage is based on the volume of solute per 100 milliliters of solution. Other important terms include molarity, which is the number of moles of solute per liter of solution, and molality, which is moles of solute per kilogram of solvent. Mole fraction expresses the ratio of moles of a component to the total moles in the mixture. For very dilute solutions, parts per million ppm and parts per billion ppb are used. These different measures help chemists accurately describe and compare solutions in various contexts, from laboratory experiments to industrial processes. Solubility is a crucial concept. It tells us how much solute can dissolve in a solvent at a given temperature and pressure to form a saturated solution. For solids and liquids, factors like the nature of the solute and solvent and temperature play significant roles. The rule, like dissolves like, means polar solutes dissolve best in polar solvents and nonpolar in nonpolar. Temperature can either increase or decrease solubility, depending on whether the dissolution process is endothermic or exothermic. For gases and liquids, solubility generally decreases with rising temperature but increases with higher pressure, as described by Henry's law. This is why cold water holds more dissolved oxygen, supporting aquatic life. Understanding these factors helps explain everyday phenomena, from why sugar dissolves faster in hot tea to why soda fizzes when open. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid in a closed container. When a non-volatile solute is added to a solvent, the vapor pressure of the solution drops compared to the pure solvent. This phenomenon is explained by Raoult's law, which states that the partial vapor pressure of each component in a solution is proportional to its mole fraction. For ideal solutions, this law holds perfectly, but real solutions often show deviations, positive or negative, depending on the interactions between components. These deviations can lead to interesting effects like azeotropes, mixtures that boil at a constant temperature. Understanding vapor pressure and Raoult's law is essential for fields like distillation and the beverage industry. Colligative properties are fascinating because they depend only on the number of solute particles, not their nature. These include relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure. For example, adding salt to water raises its boiling point and lowers its freezing point, which is why salt is used to melt ice on roads. Osmotic pressure is especially important in biological systems, as it governs the movement of water across cell membranes. Sometimes the observed effects differ from expected values due to phenomena like association or dissociation of solute particles, leading to abnormal molar masses. The Van Hoff factor helps account for these differences, ensuring accurate calculations in real-world scenarios.